So we'll be reviewing a few more historical geology aspects of the course today. And then there was just one other thing that I wanted to do. I had a poll that I was going to run, and how do I launch that poll? Hey, Stephen, are you there still?
Oh, can you hear me?
Oh, there we go. Yeah, I can hear you. Can you? And I just can't remember how you initiate a poll on this Zoom software. Do you remember?
Yeah, you should have on the bar
Oh,
across the bottom, a poll should be an option, but I don't see it there for you.
okay, I've got it though, because I'm hosting. But
Yeah,
when I press this, I can add a question, but I can't launch the poll. Oh, maybe I have to click on it.
you have to click on it, add the question, and then indicate the answers, and then you can launch it.
Oh, okay. I did that already, but I think I did it wrong. So I'm just going to have to move on from there, and that's okay. We can quiz them next time for sure. Well, actually, we can have an open quiz. There's a background behind me. That's from the movie Wayne's World. What song are the gentlemen, so to speak, in the car singing? You can type in your answer. What song were they singing in the movie for this scene? This is for bonus points. Oh, okay, Dawson gets it. Joey got it. Yep. Bohemian Rhapsody question mark. No, that's exclamation mark, Dawson. And Bohemian Rhapsody from Joey. Yep, yeah, you're the first two. So duly noted. That's probably an extra 2% on your final grade. Just kidding, of course, but that's all right. Okay, we're going to carry on with some historical geology now. I'm going to share the screen to the tablet. And we should be where we left off last day when we went for a little tour of Jasper National Park to look at different examples of the rock record Quino. Yes, absolutely. That's right, Margaret. Also a bonus point for getting the group right. And then we left off, I had some slides that I think they're really basic. They come from your first year courses. Any of you that have taken 100 or 201 are familiar with these. I'm just going to talk briefly about their significance, and then we're going to move on to the geology of Western Canada and talk about things that are a bit more interesting and challenging in their own way. And it should be a fun lecture from that point of view. So we want to talk about the principles of stratigraphy and historical geology. Historical geology isn't what it sounds like, which is a history of geology. Historical geology is the history of the earth. That's what historical geology is, meaning from 4+ billion years ago to now, the story that the rocks in the rock records tell us. And there's many ways that rocks tell us stories. They can tell us things by their chemistry, and that might relate to the composition of the oceans they were deposited in. They might yield information from their fossils and tell us something about the life that was associated with those ancient rocks. But also just their state of deformation or not deformation tells us a lot about the tectonic history. And the tectonic history is the history of the continents moving around at the Earth's surface in relationship to subduction zones and extensionary boundaries. So the rocks have a history to tell, and historical geology is the art of understanding it, I think. The first person to really get a grip on the idea that rocks had a history was Nicholas Steno, Danish. And he gave us three principles in the 1600s that no one had really considered before then. And it was such a leap of abstraction that I find it amazing to think that you could look at mountains and really come from an education and a framework background that was understood that the world was created as opposed to the sum of a bunch of evolutionary forces. And as such, he he had, I would say, a little bit of a vision. And the first principle Nicholas Steno proposed was that the principle of superposition, which is in an undisturbed succession of strata, in other words, under normal conditions, the oldest rocks are at the bottom and the youngest rocks are at the top. Now, if you've never been told this, it's not necessarily intuitive, because the first thing you have to understand then, if the youngest rocks are on top of the oldest rocks, is that the rocks are laid down progressively in layers. And at this point in the history of Earth science, it wasn't clear that the Earth was laid down in progressive and successive layers. So the idea that younger strata occurred higher in the rock record was quite revolutionary. And it's a fundamental basis on which we interpret sedimentary rocks when we observe them in the field. So here's an example from Western Canada near the Athabasca Glaciers at Saskatchewan Crossing. And you can see that we have older rocks, and you don't necessarily know the age of these rocks, but on the lower left, the Sullivan, Lyle, Bison Creek, going upwards into the Skokie, Owen Creek, Mount Wilson formations, but just an example of younger rocks residing over top of older rocks in the Canadian Rockies. And we'll get back to that. Nicholas also suggested that rocks were initially deposited horizontally, and at least on some scale, that's true. And again, it showed a cognizance of the fact that rocks were in some way, shape, or form laid down as flat layers. And originally, these layers were horizontal, or at least close enough to horizontal to be taken as horizontal. There are exceptions, and maybe we'll talk about that in a couple of slides going ahead. But you could imagine, for example, the bedding surface of a steep alluvial fan. That bedding surface, the top of the alluvial fan, is not horizontal. It builds out laterally over time. And so it has what we call some type of accreting front. So if we had an alluvial fan, let me just get rid of this. So if you had a mountain and it was shedding off, hang on. So here's our mountain and it's shedding off sediment, and that sediment is building up as some type of alluvial fan, then naturally there's a dip to the sedimentary surface there, and it's not being laid down as horizontal sheets. But the sedimentary package more or less approximates a horizontal sheet. And that's what Nicholas Steno's observations in the mountains were showing him, were these packages that had laterally and vertically accreted over time, forming these tabular units. And here's an example from, well, it's near Nordegg. It's west of Nordegg, Alberta. It's near a place called Landslide Lake. We used to run a field school out there a few years ago, and these are Cambrian aged gravel beds. And these Cambrian beds are now dipping at about 45 degrees to the south and west. And you can see there's nice gravels in the rocks. These gravels are forming a conglomerate. I think I'll change that color. A conglomerate. And there's sandstones, which you can't see because you don't have a hand lens, but everything in between here is sandstone. But these are nice, very highly dipping beds from the horizontal, and they were originally lied down horizontally. Kind of thoughts that we take for granted these days, don't we? And here's Old Fort Point. That's one of my old photographs from about 1998 or so. It's an actual film photograph. You don't see many of those anymore. But remember, we stopped there at stop one for our little field trip on Monday, and the bedding was very steep there. And you can see here that the bedding is steep, and it's actually even folded. This is part of a limb of a large fold that it's a limb of a large fold that you can't see because part of the fold's now missing out of the field of view. It's been eroded in part, and all you have is the bedding in this limb that's vertical. But it's kind of interesting to think that there was a time that those sediments were at the floor of an ocean and formed an ocean floor bed, and that was more or less horizontal. And here's another one of these exceptions, the principle of original horizontality. These are Aeolian dunes. The Aeolian dunes migrated from left to right, and the dunes were from some desert setting. And if we just blow that up a bit. Lovely. You can see what are called foresets. Oops. Foresets here, toe sets here. These migrated laterally over time in response to the wind in the desert. And so they record a direction of movement of the dune as a rule. And so these are called paleo current or paleo wind direction indicators. So this is an example from an Aeolian dune, in other words, in a desert, but you get very similar bed forms underwater as well, of course. And so these are not deposited horizontally, but again, it's a bit of a trick question because the beds that they are deposited in form originally horizontal units, and that's what you need to understand and remember. And then there's Nicholas Steno's final principle of lateral continuity, and that's that beds are conceivably endless. They go for large distances in 3 dimensions laterally. In other words, it's not that normal to have a small rock unit that's at the formation scale. I mean, I think there's exceptions to this rule, but the idea that these rocks were laterally continuous is actually really important, right? Because it gives us the ability to map these rocks if we understand that they're laterally continuous. And it might not be evident immediately that you need to understand what lateral continuity is to map rocks, but if you can understand that a rock is literally a sheet of rock, and that sheet has a 2-dimensional or 3-dimensional distribution in an area, then you can predict, if it's deformed or undeformed, where that rock will occur next. And that's the whole basis of geological maps. So we're going to get back to geological maps in about 10 slides, and we'll get back to the concept of lateral continuity at that time. And you'll see when we're looking more closely at geological maps than you normally do, that the concept of lateral continuity is actually a pretty critical one. Anyone know where this photo is taken from? Anyone want to take a guess? Type it in for bonus marks. Yell it out for more bonus marks. Drumheller, Margaret's got the fast trigger hand there. Oh, Jax is pretty quick. Bad spelling. That's all right. We're not. It is bad spelling, but it's pretty fun spelling. That's all right. Hoodoo's not. Yeah, that's true. It's not. It's not at Hoodoo Provincial Park, which we'll look at later in the course, but it's near the Hoodoos, and those are Hoodoos of some form, I guess. I think that's fair enough. Yeah, that's right. So Drumheller. So yeah, if that's Drumheller, then probably those stripy beds are what we call the Horseshoe Canyon Formation. That's normally what we have there. And I'll just throw in these incidental things as we go on, because you're going to learn about the stratigraphy of Alberta anyway, and this will give you a head start. And it's Cretaceous in age. It has some vertebrate fossils in, like dinosaurs and whatnot, but it's not the most fossil rich from a vertebrate fossil point of view. And then there were other people who contributed to our understanding of what stratigraphy can tell us. James Hutton, he really was a uniform. The James Hutton was the person who proposed uniformitarianism, the idea that you could use observations in modern settings to interpret the context and the processes that were occurring in the rock record from the rocks. But he also talked about the principle of cross-cutting relationships. And the idea with the principle of cross-cutting relationships is, if, so remember that Steno said that this rock on top had to be younger than this rock on the bottom. So younger is over older in that case, and it should be, right? But the Y rock there isn't the youngest rock. The youngest rock is the one that cross cuts it here. And so the youngest rock that we can see in this field of view is in fact this rock here, that rock unit, because it truncates everything. And in a nutshell, that's what the law of cross-cutting relationships really is. I was going to draw a diagram for the principle of cross-cutting relationships, but I think I'd be wasting your time, because I'm hoping you understand that already. Now, if you don't understand this principle of cross-cutting relationships, feel free just to type it in to your text. You can even do it anonymously to me, anonymously to me, if you don't want the rest of the class to see. But if I can go on, I'm going to give you 5 seconds to consider this. Just say no if you need a better explanation of this principle. Okay. And then very similarly, the law of inclusions, and it's like a cross-cutting relationship, but essentially a pebble must be older than the rock it's in if it's a sedimentary rock. So the law of conclusion or components or whatever. And that doesn't, I mean, we don't look at rocks at the scale in this course, but I wanted you to kind of understand how we understand the relative ages of these rocks and how we put them into a framework of youngest to oldest or oldest to youngest. The other aspect of stratigraphy and the historical geology I want to talk about before we talk about geology of Western Canada are unconformities. And you should all remember what unconformities are. These are surfaces of erosion. Functionally, they're stratigraphic levels where rock is missing. Okay, so you might have rock that's very old, maybe Cambrian rock that's 541 million years old. And then maybe there's an unconformity on it, and the next rock is Cretaceous, and it's 132 million years old, right? That means then that we have 412 million years missing. That's a big unconformity. Why are unconformities important in the rock record? I think you want to think of them like punctuation, right? You know, when you have punctuation in a sentence, it's setting aside related aspects of the rock record, and unconformities show where the disruptions are. So in between unconformities, we view the rocks as having more relationships with each other than across unconformities. And that's important because of all the ways we interpret rocks, their relationship to the most adjacent rocks is one that we use for a lot of perspective, right? So that evolution from one rock type to another rock type with an evolving fossil content or lithology is a large part of the framework that we use to take apart the Earth's history. If we're going from deep sea environments to shallow marine environments, what happened? Was the land going up over time? Was the land building out over time? Was sea level dropping, right? Like was glaciation going on and it brought sea level down 200 meters to the shelf edge? These are the questions that we answer by looking at the evolving packages of rocks. And so when rocks are interrupted by an unconformity, we cut our losses. That's it. That evolving relationship is at its end. So that's why unconformities are important. And in EAS 100 and 201, we spend a lot of time, I think, discussing the importance of unconformities without ever really telling you why we think they're important, which is a bit of a pity. We're going to get back to this, but functionally, I've said it already, an unconformity really is a missing time in the rock record. And here, this is the great unconformity at Sicker Point. And James Sutton came away with the idea that there's a time gap here when he observed that beds were oriented this way, and then beds are oriented this way. That's an angular unconformity, and it's a whopper of an unconformity, and it's a beauty because anyone can look at that unconformity and appreciate that this is there's missing time there, meaning that these rocks are all related to time X or whatever, and these rocks are all related to time. Yeah, well, we'll just go. I don't want to go Y. B. And so all of these rocks are more closely related to each other, and all of these rocks are more closely related to each other than they are across the unconformity. A bit of common logic there, I think, for you, but it's such an important framework in which we interpret the rock record that you can't really take it for granted, and we wouldn't want you to do that. Grand Canyon, this is from your first year textbook, The Blue Planet. It's an image of the Grand Canyon with the great unconformity cutting through it. And so what is an angular unconformity? It's exactly that. Tis when tilted rock has been uplifted. We say uplifted because you need to uplift things and expose them to subaerial erosion before they'll erode. And then on top of that is horizontal strata of some type. And it does not matter which, does not matter what lithologies these are. Just as a note, I'll point out that normally we indicate an unconformity with a red squiggly line. So that's a convention, okay? So by convention, an unconformity is indicated as a red squiggly line. And quite often, if the cross-section is made correctly, you'll see unconformities indicated that way. I think the more I look at modern drafting, people are getting more and more away from it, but that convention's useful because you can interpret the schematic with your eye right away, and you'll see examples of that. So there are angular unconformities. There's the Western Canadian Sedimentary Basin has very large scale angular unconformities that at the local scale can't be observed as angular unconformities, but at the regional scale certainly can be observed as angular unconformities. That'll be, I'll prepare a slide for you in about 4 or 5 slides discussing that. And then a disconformity is seen as a contact between strata whose ages are significantly separated, but the contact is more or less horizontal and the rock units are parallel. And a nonconformity is seen at the contacts between crystalline rocks and sedimentary rocks. And so what I would say by way of an explanation there is that you have crystalline rocks. You could think of granite where do we have granite in Alberta? Does anyone know where there's abundant granite or nice other rocks like that, crystalline basement rocks? Where do they occur in Alberta? No one? No guesses? Below the mountains. Well, actually, okay, great answer, Jax. Banff, not so much, but yes, below the mountains in Banff. But where could you go have a picnic on an outcrop of granite in Alberta? Well, on Friday, you're going to go to Wood Buffalo National Park, and we'll look at some slides with guest lecturer Professor Tom Chaco, who's done research up there off and on. And there they have granites and gneisses and even migmatites, highly sheared metamorphic rocks. Also some very old sandstones. There's some very old strata in Wood Buffalo National Park. Not many people are overly familiar with it because you can't just up and drive there, which is too bad because I think that'd be great. The sedimentary rock goes over all of this. And so what separates the granite and the sedimentary rock is a nonconformity. So that's what this is. And could you argue that we should show that as a squiggly line? If we're doing a cross section, then absolutely this is a better way to do it. Whoops, oh well, I missed a little bit. That's all right. And here's some examples. I mean, this is up from that direction. This is Great Plains Lubicon Lake, Little Buffalo. This is in our museum, by the way. A sedimentary rock over a gneiss, and you can see that's a nice non-conformity right there in our rock museum, which under normal conditions I could send you down to view yourself. And right now you can't. But when things are back to normal, you shouldn't hesitate to go to the Earth Science Building and the basement. And there's both a fossil museum and mineral museum, mineral and rock museum, and the collections are super fantastic. Much well worth seeing. But there is a nice non-conformity for sure. And then let's just put this together in the Western Canadian Sedimentary Basin context. And that's like this. Now, the Western Canadian Sedimentary Basin, if we were to go back to considering Alberta, the Western Canadian Sedimentary Basin kind of sits right over top of Alberta. It actually shoots off to the north and continues on to the south, to be fair. That's more or less where it resides. And one of the things that you understand, I think, is that there's mountains here and the sediment is infilling the basin here. So this axis here is the deep part of the basin. And so if we were to do a cross section of the basin, like this, it would look something like this, where the lowest part of the basin is onto crystalline basement. And this is why Jax was right about there being crystalline basement in the mountains. There actually are, you get into BC, there's no shortage of granites and granitoid rocks in out there. So it's not a bad answer. But on top of this unconformity is the Western Canadian Sedimentary Basin. And then below it, we're just for the sake of simplicity calling this crystalline basement. And then remember, this is then A prime, and this is A. So A is to the southwest. Within the Western Canadian Sedimentary Basin, for sure, there's sets of unconformities that contain Precambrian sediment, Proterozoic strata, but we're just going to go pre-C, pre-C. And there's three major unconformities associated with the Precambrian. And then there's also the Cambrian strata itself. And one thing that you'll notice, I've already shown you something that is not intuitive, and that is that the basin is very deep over here to the southwest, and over here to the northwest, it's quite shallow. Northeast, I should say. It's the edge of the basin. And that's because the weight of the mountains has kept progressively over time, the weight of mountains and sediments have tectonically pushed this side of the basin down. So this is tectonic and sedimentary loading. Which is causing some type of isostatic effect, pushing the crust down and allowing it to thicken over time. So we have literally 10, 15 kilometers of sediment to the southwest and zero at the edge to the northeast. Okay. The Cambrian package is next, and the Cambrian package has rocks that I'm drawing regionally like this that have a stratigraphy, okay? So these are Cambrian rocks. And on top of the Cambrian rocks is a subaerial an angular unconformity that truncates the Cambrian rock. And this happens for almost every major division in the Western Canadian Sedimentary Basin. There's an Ordovician unit that's cut off near the mountains. There's not much in the way of Silurian, but there's a big Devonian package that's held within an unconformity. There's another unconformity that holds the Permo-Triassic, Permian-Triassic wedge, and another unconformity that's at the base of the Cretaceous, and another unconformity that's at the top of the Cretaceous. So if we were to go into our geological times, we would have Ordovician here. Ordovician, Devonian, and we'll hook the Mississippian into that sliver as well. And then this can be the Permo-Triassic. And this can be the Cretaceous, and this can be the Cenozoic. And all of these are angular unconformities, but regional unconformities. Over time, they're progressively pushed down that way. And that's why they're all angular like this. And they're regionally angular, which has really massive consequences for oil and gas migration in the Western Canadian Sedimentary Basin over time. And we'll get to that later on in the course when we're talking about the Devonian, the Mississippian, the Triassic, and Cretaceous, which are most oil-prone and gas-prone levels in the Western Canadian Sedimentary Basin. So that's the story of the unconformities in the Western Canadian Sedimentary Basin. And it's kind of interesting to see just how well punctuated it is over time. And, you know, it's no coincidence that it's, you know, these geological systems like the Cambrian or the Cretaceous or the Devonian are enveloped in their own stratigraphic packages that are unconformity bound, because there's without a doubt a stratigraphic equivalency globally to these units, which is why they were named in the first place. And I think it's got a lot to do with the history of sea level going up and down over time, something we haven't discussed a lot, but you know, and that effect of sea level going up and down over time is a large driving force in causing these packages to occur all over the world. So that's one thing. So the cycles we should ascribe to processes like long-term sea level change. And what drives sea level changes? Well, things like mid-ocean ridge spreading rates, things like whether or not there's continental glaciers being formed at that time, and probably aspects of climate and continental position. But the other thing that's driving the bus and related to sea level change are these things that are related to tectonics. And you might even include at the largest scale the idea of Wilson cycles, which are named after a Canadian geophysicist, Tuzo Wilson, who worked out of the University of Toronto and proposed that continentals assembled and unassembled repeatedly over time. And the idea was that these were happening on the orders of hundreds of millions of years and were driving some of the great stratigraphic correlations, the greatest stratigraphic equivalence that was driving the bus on the equivalency of strata all around the world, the idea of Wilson cycles. And, you know, there were examples, you know, because in the Precambrian, the first supercontinent is Rodinia. There's actually one older than Rodinia, but that's the one most recent in the Precambrian that we know about. Then, of course, there's Gondwana, Pangaea, and these are the assemblages and disassemblage of these large-scale cycles. The edge of the base, which is causing some type of isostatic track. Seems like my microphone is recording what I'm doing. It was just recording what I'm saying and converting it to text. So it looked like a question, but it was just me talking back to myself. Haha. All right, there we go. And in a nutshell, that's kind of our story of unconformities in the Western Canadian Sedimentary Basin. And it's a good preliminary spot to break into the notes that I downloaded or uploaded onto eClass today, and that is the geological framework of Western Canada. And that are the slides that look like this. So if you want to look for these slides and download them, that's fine. I'll also be uploading these annotations. This will have a lot more annotations than we did before. I want to emphasize again the effort of Dr. Fred Clark, who developed this course over the years and passed off the notes to me. I've readapted them to suit my view of the geology of Western Canada, but his notes were certainly helpful in providing a framework. I want to first talk about geological maps, because geological maps, if you can take them with you to a national park or to a part of Alberta, they're incredibly informative resources to help you look for and predict the distribution of rocks. And remember, a geological map usually is a map that tries to show the distribution of geological units, and the geological units are always portrayed in a legend as the oldest all the way up to the youngest. So oldest up to youngest, and they'll normally be assigned some type of color. So you might have a green Precambrian unit, a blue Cambrian unit, a purple Ordovician unit, and maybe a yellow Cretaceous unit up here. So there's nice big unconformities somewhere around here, but in fact there's probably unconformities between all of these, because that's usually how it goes. And so then you have a map that has contacts on it, and the contacts separate these units. And the thing is, we quite often take for granted certain aspects of geological maps, and I'm pretty certain most of you have. Izam is asking if I have the document available as PowerPoint file. Right, I do, but you can't have it right now. So do I read this right? You'd rather I just post the PowerPoint going forward? Or does the PDF not do the job, Izam? Oh, okay. I can make sure I the PDFs I usually, yeah, okay, the PDF I usually can usually lower the file size if I'm conscientious, and I never thought about it today. So well, let's take a little break and I can email you the PowerPoint from today. Let me just get that for you. So what I'll do is I'll stop sharing and I'll email the group that PowerPoint, because I did email you once today already, so this will be easy. Isaac, it won't take me a second to get these notes, so it's no problem. I'll just email them to you guys right now. I'm on my way to doing it, so that's fine. I needed a break anyway. My brain was starting to play tricks on me. For some reason, my internet is, oh, it's probably just, uh, yeah, you're on your own, Isam. The email's just barfing probably because I've got Zoom and Google Earth and everything open for the lecture. So I think my computer is just sad. Okay, so we're going to go back to business here. Okay, I tried, right? Okay, sharing the screen. Where were we? Yeah, what is a geological map, right? That's where we're at. I'm hoping you all remember from your EAS 100 lab what a geological map is. If you took 201, it might be a little tricky, but you mostly all have seen a geological map, whether you've known it or not. You'll have these black lines in them. And in between those black lines, you'll have the color of the geological unit indicated. And usually these maps are very beautifully colored and so on, okay? And they normally occur in some kind of order unless there's a disconformity or an unconformity below between them, right? So that's a geological map. And on a geological map are symbols that help you understand the map. And let's say, for example, we had yellow here. So we have a normal succession up here, but an odd succession here. Then there's an unconformity between these. And what you'll commonly have is these maps. And there's such a thing as a dip symbol. That's showing you which way the rock beds are dipping. In other words, it's dipping towards the direction of that tick. There are also features that might be faults, right? So let's say this wasn't an unconformity, but it was a fault, and it might be a thrust fault. And a thrust fault would be indicated. So it's separating the green unit from the yellow unit by a fault. So the green unit is being thrusted on top of the yellow unit. That makes sense because the green unit's older than the yellow unit, so it had to get on top of it somehow. There's also folds, and the rock is kind of funny shaped here, and maybe that's because it's folded. And we show folds by showing the crest of the fold as this line here, and the direction that the limbs go in. This is a syncline here, so we have syncline, meaning that the legs bow up, and we have anticlines or antiforms, meaning that the legs bow down. So in an outcrop, an antiform or anticline looks like that, and a syncline or synform looks like that. And so we use all of these different symbols to view and appreciate geological maps. And what I wanted to do was just take a few minutes to look at a geological map with you, because geological maps have so much information for us to view. And here we're on Google Earth, and we've got one of the geological maps from Jasper National Park shown on the Google Earth view. And I put it here on Google Earth because seeing how it relates to the topography is useful. For starters, this is called the My Map Sheet It was made by the Geological Survey of Canada in about 20, 30 years ago now. And oh, it was only, I don't know when it was it's copyright 2010, so it's not that old. And just do this. This is the map header here. It's draped over the topography, which is why it looks funny. That's the scale. The scale is always really important. 0 to 1 kilometers here, so you can get a sense of the scale of the map. 1 to 50,000 isn't a big scale map. It's not a small scale map. It's somewhere in between. These are mountain ridges and mountain ranges, so you can get the sense that these are fairly big geological units. And you can see that they're presented in some order. So here on the right, we actually have Precambrian. There's very little Precambrian on this map, maybe just a little bit on the most southeast corner of it. I'm not even sure that's true. Cambrian rocks all the way up to here, Devonian rocks here. And you can see they're all indicated by color. You're probably pretty used to that. It's pretty common for the Geological Survey of Canada and the Alberta Geological Survey to show Cretaceous units as yellows, browns, and greens. And they followed that convention here. And then you can see that we have all types of little ridges. And these ridges we can have a closer look at. You can see seem to be separated by a bunch of faults. And that makes sense in the context of what you already probably know about the Cordillera, and that is that the mountain ridges are thrusted sheets of rock that are piled on top of each other. And in some cases, the rocks fold as they get pulled up in those faults. Here's an example at Folding Mountain, where there's an anticline, and these different geological units are being displayed in various ways. And then you see the rocks are dipping to the left here on that side, and on this side, the rocks are dipping to the right. That's a very typical anticline. And I'm not showing you this so you understand the geology of Jasper. I'm showing you this so you understand that you can use a geological map to tell you something super cool about the rocks. And that is, where can you predict that those rocks will occur? And that is important. I think there's a knee-jerk reaction to look at this rock and to say it's a map of the rocks. And in part, that's true. But most of what's showing there is underneath soil, grass, and trees. In other words, you don't know that rock's there, right? That rock is a prediction, and that's the whole point. This whole map is predicting the distribution of geology. You see all of these dashed lines here? That's a prediction. It means that we're not sure the rocks are there, but they should be, right? If you looked at a geological map of Edmonton, you'd see that, for example, underneath the till here, we predict there to be Edmonton group strata that's Cretaceous, right? But it's a prediction. Until you drill a well, you don't know it's there. A geological map is for predicting things. And this gets to the idea that rocks are initially horizontal, might be folded, but have a huge lateral extent, because that huge lateral extent lets us use geological units as planar bodies that have been folded and therefore have a geometry, and that geometry is predictable. Then we solve problems like, if we have a geometry of a rock unit that's folded, like an anticline, and there's a topography that cuts into that anticline, what will it look like? And that's what these cross sections that they show commonly on these maps are all about. They show you something about what we think about some of the assumptions about the geology. All the unit thicknesses are pretty much the same throughout here, right? We don't know that. We haven't gone and measured any of these rocks. We actually have no data from here whatsoever. This is based on no data. This is an interpretation and a prediction of what the rock should look like as you look at these different lines of sections across the map sheet. So when you really look at it, what an abstraction. And most geologists absolutely love making cross sections and geological maps, because it's an abstraction, it's a prediction, it's fun, and you do it off of field data. And the field data that you use might be very limited, right? You know, for example, we know where the data is when this map was made. How do I know where that data is? Let me show you a little trick here. Wherever there's a strike and dip, that was measured by hand by a compass. So like that one there, that little strike and dip, that was measured by hand by a compass. So the person who made this map, Eric Mountjoy, was at that location. Okay, but look, he wasn't over here, but he still drew the rock in, right? And then if you go further back, go to some of the hard to get areas here. Oh, sorry about that. No soon error. See, lots of units here, especially this one that's under, it's at the valley bottom, right? And look, there's a Jurassic unit that's in association with the river down here. And you can see it's all dashed in. There's hardly any measurements except where it's exposed at the riverbank. So very limited data that's based upon. But this is like all geological maps. There's limitations to the data that we can use, okay? Or that we have access to. So that's a geological map and a cross section in a nutshell. And then what I want to do here is go back to the notes. And here's an inset from that same geological map. I just like using it on Google Earth where we can drape the topography. There's the cross section. See how detailed the legend is? Has the lithologies. Sometimes it'll indicate characteristic thicknesses. And the thing is, you can use this map when you go to a national park, if you're, or a provincial park, and you know somebody tells you that, you know, the Eldon Formation has lots of archaeocyathid fossils in it. Well, you can go look for the outcrops of Eldon Formation and see if you can find archaeocyathid fossils, which are kind of like early sponges. So in a nutshell, that's kind of the deal with geological maps. And then I just really wanted to start talking about then what the geology of Western Canada is all about. And the reason we talked about the geological maps is we're going to look at a lot of geological maps throughout the course, so I want you to be comfortable with those. Right, the Western Canadian Sedimentary Basin. There's five geological provinces that are related with Western Canadian geology. One is the Western Canadian Sedimentary Basin. One is the Amaneka Belt. Then there's the Intermontane Belt. The Coastal Belt. And the Insular Belt. Also to the east are the non-sedimentary rocks, although some of them were sedimentary at one point, but the most metamorphic and igneous rocks of the Canadian Shield, okay? So these are the main units. And just to have a brief description of these units. Oh no, I'll get right back to that actually. Okay, that's where I want to go. Okay. Okay, so those are the main units. Now we can go back to Google Earth then, and I'll just stop share here. So that's the Alberta bedrock map. It's called like AER 600 or something like that. I actually uploaded a copy of this map into eClass for you, so you'd have your own copy of it. The province gives it away for free, and it's available online as a PDF and a JPEG. It's an excellent map, really, and it shows the geology of Alberta. And you can see first and foremost what is the Western Canadian Sedimentary Basin, which is all of this. Okay, that's the Western Canadian Sedimentary Basin. And then we have the deformed mountain belt front right here that contains the front ranges and the main ranges. And then in behind here is the Amaneka Belt and the Intermontane Belt and whatnot. Up on the right here is that Wood Buffalo National Park, right? Woo. And I didn't include the legend on this map, but you can see here that the codes that they give it, like P, Precambrian, PRR, Archean, AP, Devonian is D here. So there's nonconformity in here that they've not shown with the squiggly line, which maps that's common not to show the unconformity is a squiggly line. So that's Wood Buffalo National Park, and that's the bit of shield that Alberta has. And so Alberta actually has a pretty diverse geology, right? It goes from shield to the Western Canadian Sedimentary Basin and over to the mountains, and it has the front ranges and the main ranges. And if we took a close look at the geology of Alberta, there's areas that are interesting. This is, it's worth noting that the youngest rocks are here, this yellow unit to your lower left. I hope you can see the hand I'm moving around. And then the rocks get older and older and older to the right until at the very edge of the, sorry, I'm using a magic mouse and it keeps doing this magic zoom that I haven't quite figured out. It's very frustrating. So the Devonian rocks are up at the edge of the basin, and the younger rocks into the Triassic and the Cretaceous all go towards the son of the sun. Oh, I'm gonna get so crazy. To the southwest. Okay, there we are. So you can see the basin. Fort McMurray's over here in the Cretaceous rocks. It sits right on the Devonian rocks. There's a Devonian basement at Fort McMurray, and then the resource of the heavy oil is all in the McMurray Formation. Edmonton's down here somewhere, and then you can see that's the Edmonton Group strata that we're sitting on. And then you get to the mountains, and it won't surprise you anymore to see that the mountain ridges are all separated by these thrust faults, and we have many thrust faults, and this is all owing to the idea that there was compression from a subduction zone to the west of North America, and terrains were accreted onto and moved along the faults of Western Canada, pushing them back and deforming the rock and doing what we call shortening the rock. And in shortening the rock, you accordion it and you make all of these thrusts and folds. And that's the origin of the mountains for sure. And so if we want to first look at some of the rocks of the Canadian Shield, there's lots of nice rocks in our museum that show these: biotite granite from Fort Chipewyan, red granite from Fort Chipewyan with a little bit of, probably a little bit of plagioclase in there as well. Might not be a true granite. Foliated granite, if it's foliated, maybe we're starting to get something like a gneiss, and the gneiss has a nice layered look to it, but it's a crystalline rock that's been metamorphosed, or it can be a sedimentary rock that's been extremely metamorphosed and recrystallized. Um, More gneiss, and this is a view of Tulip Lake from the air where you can actually see the granites outcropping up by Great Bear Lake. I have a video that I took from Google Earth at the end of this, and we can have a look at that when we're ending up our day today. Here's some nice foliated rock from one of my good friends, Suman Day. He was doing his master's up there back in the 90s. He was a good pal of mine, and I got this picture from him ages and ages ago. And then this is kind of showing what the relative ages, the absolute ages, I should say, of these different rocks of the shield really are. You're not, I'll save you the bother of studying this. This is not on the exam. Um, these dates are not on exam. But maybe that this tidbit is a bit more important there. So getting back to the major elements of the Western Canadian Sedimentary Basin, the Western Canadian Sedimentary Basin is itself contains rocks or strata from Precambrian through to the Pleistocene, we'll say. Largely sedimentary rocks, but not exclusively. There are some Precambrian sills and dikes, and there's some Cretaceous volcanics in the Western Canadian Sedimentary Basin as well. But they're certainly limited in their distributions, and they're not the main rock type. The Western Canadian Sedimentary Basin certainly is dominated by shale, limestone, and dolostone carbonates, but also sandstone. In general, it's been accumulating sediment through various basin morphology stages. It was more of a passive margin. Up to the end of the Permian. And it became what we call a foreland basin after that. From the Triassic and onwards. And some people don't necessarily view the foreland basin stage of the Western Canadian Sedimentary Basin as truly starting until the Jurassic, and there's good stratigraphic and geological reasons for making that assertions, but the things start changing in the Triassic, so we'll just split it up there for our purposes. I think that's fine. And so the Western Canadian Sedimentary Basin has the most complete history of the geology of Western Canada, and is very, very well studied because there's so much oil and gas interest in it that there's almost no geological unit in the basin that's left unturned. And so there's a nice history of geoscience conducted on that. Then we have, just by way of summary, I know a lot less about these units, but there's the Omanica belt. And it's a metamorphic belt. I think we normally say it's highly metamorphosed. And all we mean when we say that something's metamorphosed is that it's been either heated um, such that it's changed in its crystallinity or composition in some way, or it's been under such pressure that it's changed, or both, right? So heat and pressure are the ingredients for metamorphic rocks. And there's it's composed of fragments of North America that are variously aged. So there's fragments from on the order of 2 billion years ago to BA 2 billion years ago, up to about 180 million years ago. Million years, remember, I like to use MMA. That's thousand annums. That's 180 million years. So that's my preference. Yeah, and it has different terrains. I don't remember the names of all of them. Slide Mountain terrain, the Yukon Tanana terrain, and the Cassiar terrain. So these are kind of accreted or imposed along this kind of subduction area where we were bringing island arcs and whatnot into the margins of Western North America. Then there's the Intermontane Belt. Intermontane Belt is flatter. I think it's lower elevation. It's kind of rounded. It's composed of. I remember from field school. We used to do third year field school out there, and I did it as a student, not as an instructor. But there's like the Cache Creek terrain, the Stacania terrain, and it's a lower metamorphic grade, but it's still metamorphic. And it's kind of ranges. It has a big range from rocks that are pre-Devonian, 400 million years old, up to about, even there's volcanism up to 10,000 years ago within it, which is kind of mind-boggling when you really think about it. That just 10,000 years ago, you could have had volcanic activity as near as the Intermontane Belt. And if you want to visit these, I think we'll try get some pictures of this later in the course. But like, there's the Nazca Cone and something else, Satah Mountain, Satah Mountain. So pretty cool. And then there's the Coast Belt. And I won't say I know a lot about the Coast Belt, but at least I've spent a lot of time out there and I've got to enjoy the geology a little bit. And there's a lot of granite, granodiorite. Don't worry about the difference between granite and granodiorite. It's a feldspar composition by large part. And I think for the purposes of having an interest in the geology of Western North America, and particularly Western Canada, and what you might see in a park, I don't think you'll impress your husband or wife if you're like, oh no, that's not a granodiorite, not granite, it's a granodiorite. So you probably just shouldn't even go there, right? Yeah, that was I'm just going back to Nick's question, Nicholas' question, 2 billion to 180 million years. Yeah, that's right. If that's a question, Nick. Yeah, that's right. That answer your question? Ah, wonderful. Okay. If you guys ever get bored, just cut in with the mic. I really don't mind at all, and it's nice to hear somebody else's voice once in a while. So I don't mind that at all. So that's a coastal belt. It was a huge outpouring of granite and one of the largest in the Phanerozoic. So it's really, it contains some metamorphosed fragments of the insular belt, terrains that are involved. So it cuts through those and it kind of rips them. I don't actually know the ages of the coastal belt that well. I think it's in the last couple 100 million years. Has maybe if Stephen's listening in, he can tell us what the age of the coastal belt is. I, for the life of me, can't remember.
Yeah, Marie, can you hear me?
Yeah, very well.
Yeah, the bulk of the coast belt granites are middle Cretaceous, so 120 to 100 million years old, but they go back to the Jurassic and get as young as Tertiary.
Okay, that's so from the all the way from the Jurassic to the Tertiary. And when was when was the most?
Middle Cretaceous,
Middle.
120 to 100 MA.
Okay, that's cool. Thanks a lot. And then, oh, my computer's doing something funny here. I'm overloading it with the software. And then finally, there's the insular belt. And that is composed of outboard terrains. They had no connection to North America before accretion. I'm not entirely sure that everyone agrees with this. Not that it matters. This is just to tell you what these things are all about. Before accretion, that's a good hint then that this was accreted to Western North America. There's two terrains that you will read about. Wrangellia is probably the one that is most discussed in the literature. Can't remember how to spell it, but we'll go with that. And there's also one called Alexander terrain. There might be other smaller ones, but these are the most important bits. And yeah, those here are about 600 million years to much younger, various metamorphic grades and stuff like that. So just leave it like that. That'll be enough for these notes, I think. What does this look like? Well, this is from your first year textbook, The Blue Planet. And this diagram is really showing, I think, reasonably well what happens as you subduct oceanic crust. You can bring other land
Marie,
masses. Go ahead.
Marie, do you want to define accretion for Jax?
Oh, goodness gracious. Oh, absolutely. Yeah. The I think I might want to find a blank slide here. I can make a blank slide actually. That's how to do it. And then you go. Oh, it's right here. Page manipulation, insert. I did it in gray just so we'd know it was inserted. So Jax, that's a really good question. And so we have, at the largest scale, we have tectonic processes that are of 2 or 3 flavors. One is that they can rift apart. In this case, the land masses are divergent. In the directions that they move. This is commonly shown schematically like this. You might have a bit of continental rock with a heat source underneath it. That heat source uplifts and dilates the crust. Finally, it starts to expand and rupture, and you build a bunch of faults. And you get what is called a spreading zone, where you're actually building oceanic crust right here. And the land masses are being pushed here as this grows over time, so that ultimately we have oceanic crust being produced that's pushing the continental crust progressively apart, and this forms oceans. So this is how a spreading ridge and a spreading zone become initiated. But interestingly, and I'll just add a and over time, you can have like the Atlantic Ocean or some parts of the Pacific Ocean where the ocean crust is becoming very vast and the land masses are being pushed very far apart. And then fundamentally, what happens is this old, cold oceanic crust ruptures or breaks somewhere along the line. And where it ruptures or breaks, so we'll have the continental crust here. Actually, let's put that a little. And you might have the spreading ridge way far away here. Back to the continental rock. But where the rock is broke, you start to develop a subduction zone. When this happens, instead of growing apart, now this spreading ridge and this continent crust start to close their distance. And so the ocean, in effect, starts to shrink. And in behind this subduction zone, depending what the orientation of the subduction zone is, you can get a volcanic arc, okay? Let's draw it the other way because it'll be easier to explain. No, that won't work, whoops. And then associated with this spreading zone is a volcanic arc. And then as this ocean closes, you bring these land masses together like that. And so instead of being separate land masses, now they become one sutured landmass. 10 out of 10 diagrams. We could do better. I presume, Angus, you're just looking for a free beer from me. Well earned, I'd say. One sutured landmass, and this is an accreted terrain. And this is the process, Jax, of what accretion is. It's really important from the evolution of Western Canada because, I mean, coincidentally, Stephen Johnson, who's in on this lecture today, just because we're interested in developing this course a little bit, is really an expert on British Columbia geology, and I'm really an expert on geology of Alberta. And I think that one general way that we usually talk about the geology of British Columbia is that accretion and compression is a big part of the geological history of British Columbia, but it's more complicated than that. And I wouldn't mind, Stephen, if you jumped in and added a few sentences to that short take on it.
Well, I'd agree that you're an expert on the Western Canada Sedimentary Basin.
But you're not going with the British Columbia bait, eh? It's a pretty, I think one of the great stories in not just Western Canadian geology, in geoscience in the last 50 years was the building up of an understanding of a geological model for British Columbia.
Yeah, no, you're totally right. The British Columbia geology is complicated because it's a melange of material that's been added to the continent at a subduction zone. So it's difficult to untangle, unlike the nice layer cake stratigraphy of the Western Canada Sedimentary Basin.
Yeah, no, from a stratigraphy and saying, okay, this is equivalent to that point of view. In Alberta, it's a straightforward business. In British Columbia, it's not so straightforward, that's for sure. Yeah, okay. So anyway, it looks like Jax is at least accepting of that answer as a general answer. So yeah, when we're talking about accreted terrains in British Columbia, there's more than one, we think, Jax, and we think this process happened a lot since the end of the Permian and onwards. And maybe even earlier, although that's heavily debated. Okay, and then, I think from a better point of view, or a more, it's really showing how these continents come together. I think that's what this diagram from the Planet Earth, your first year textbook, or 201 textbook, depending which course you took as a prereq, really shows the process of subduction, using India as an example quite readily, where you basically shrink the oceanic basin. It closes as you subduct all of your oceanic crust. Once the oceanic crust is consumed, then these two continental masses come together. Now, of course, one of the biggest one that we can point to today, would I call India an accreted terrain? Well, on some scale, it certainly is accreted into Asia. So that's a really good question, but it's accreted. I don't know. Yeah, you call it an accreted terrain. It's bigger than I think any of the accreted terrains that we would associate with Western North America. But there were some very large terrains involved with Western North America too. More than Japan scale. So yeah, it's an accreted terrain, and it was huge. But I mean, there were other examples, right? When the Appalachian Mountains were made in eastern North America, I mean, that brought Europe and North America into collision with each other, very much like India was, and the Appalachia are very much relict of the same process that you see India and Asia suffering over the last 40 million years, right? Or even, well, a little longer, but really it really gets going about 20 million years ago. And then I kind of wanted to Yeah, that's what we're at. So it's 404. Perfect. This is our chance to sketch the Western Canadian Sedimentary Basin. I've already done that a little bit with the unconformities. Okay, so I'm just going to emphasize one more time what the distribution of strata in the Western Canadian Sedimentary Basin is and its association with the foreland. I don't want to be too redundant with what I did before, but I should do it in a bit more detail and tell you what we're going to do for the rest of the course anyway. So for the rest of the course, we're going to go main geological period by period. The one that's not a period is the Precambrian. So we're going to go Precambrian, Cambrian, Ordovician, and etc. up to the tertiary. And we're going to look at the stratigraphic units in each of those. And we're going to first consider the way the world works from a cross-sectional point of view, where we have the unconformity to the crystalline basement, which I won't spend a lot of time talking about. And then we're going to talk about the units within those packages. I'll remind you that a big part of the story that we'll be getting to is the idea that there are mountains that formed to the west. And mainly for the next few lectures, we'll just be talking about the front ranges and the main ranges because they're really important in the context of some of these units that we're talking about. But those mountain ranges are the result then of this thrusting and folding that we were talking about. So if you could imagine, the way we like to draw these are these geological units that deform geometrically and predictably. And what I've drawn here is a thrust fault where the rocks have thrust over top of another unit here. Meaning that if we were to color code these rocks now, where we have a green unit, and our green unit is here. And our yellow unit which is here, and then we'll have a pink unit. Here, then that's really how these mountains are formed. And if you looked at this here, you would see that this in turn may well be stacked up. Oh, that's a bit of a twitch. And so on. And so these units over time stack on each other and they form these progressively building up ridges. And so we'll draw in the thrusts here. So here's a fault. No, I kind of missed that. I think I crossed the line there. So there's a fault. Here's a fault. These are all packages. Now just imagine what the mountain really is. The mountain is an eroded surface, right? So, you know, if your erosional surface is like this, then this is what the mountain looks like up to here, right? So we can have our colored pins and we'll color in our mountain now. We'll get in all our pink. And this is what you see when you go to the national parks or wherever. But it's what's left over following erosion, right? Not really counting my units very well. And then on top of this, this is really what's loading the Western Canadian Sedimentary Basin down here in the 4 Deep. And so we're going to be building up our stratigraphy over the courses from the Precambrian wedge to the Cambrian wedge to the Ordovician wedge and so on. So we'll do that over time. And I won't do it in detail today because I don't think I need to, right? So this gets back then to the major elements of the Cordillera. And let's just go back to our cross section. Which is shown on Google Earth. Oh, that was so unfortunate. I'm gonna have to get a new mouse to play this game, that's for sure. Flying over the mountains. There's our Maya map. But you can see very much the deformational style of the mountains here. Where I have these units that have been faulted across and these units that have been faulted up and over onto what we call, these are ramps, and then where they flatten out a little bit, those are called flats. Not great examples here. In this case, some of the flats are probably much higher up and eroded, but this is kind of the structural style that we have throughout the front ranges of most of the Rocky Mountains in the Canadian Cordillera. I really love those cross sections because they're just so interesting to look at. And then I'm just gonna go back to the sharing on the other screen. There it is. And then I'm not going to talk too much about that right now because we're going to do this with our view of the various national parks and the geological time. And then finally, we're just going to fly across the Western Canadian Sedimentary Basin in the Cordillera. So I used Google Earth to make a 3-minute film of a little trip that we can do. And we're going to start from Wood Buffalo National Park. And we're going to fly over, it's only actually a 2-minute video. And we're at Wood Buffalo National Park. That's Lake Athabasca to our lower right there. You can see we're passing Lake Claire to the right. You're flying over granite and gneisses right now, mostly gneisses, to be honest, gneisses and metamorphic sandstones. And then you're getting over the, well, at first, some of the Devonian bedrock that's associated with the edge of the margin. Hang on, is someone talking to me? I thought I think it's just somebody's mic in the background, that's fine. Oh yeah, so we're flying, there's Lesser Slave Lake, we're over Cretaceous bedrock now, we're over Valley River Group, now we're going further and further past Alberta, we're getting, in the area of Drayton Valley, so that's Cretaceous Brazeau Group, and then there's the Front Ranges, and the Front Ranges make up the first few ridges, and then the main ranges are slightly higher, larger ridges right behind the Front Ranges and around the area of Jasper there. And then ultimately you hit the Amanika Belt and then the low-lying Intermontane Belt, I guess, next. I thought the video went further than that. It's petered out for some reason. And then flying over to the west coast of British Columbia. So you kind of see the whole geology of British Columbia and Western and Alberta, just like with that overflight. It's really amazing what you can do with Google Earth. And now I've discovered you have a flight simulator on Google Earth, so you can actually go flying around in an F-16 if you want. So I wasted an hour yesterday crashing jets into Alberta. Anyway, never mind that. And so that's really it for the day. I think we can leave it at that. Here, I've got this. Let's see, are there any questions? Yeah, so Stephen, yes, the pink color represents it. That's good, okay. Any other questions?
Hi, I have a question.
Okay.
So when it comes to like after the rock, like west of the Rockies and that, why is there so many belts? Like is it just based on terrain accretion, or is there some other factors in there?
Yeah, no, I think the simple way of viewing it is that these are different tectonic assemblages that are representing different accretion phases over time. I think as a general view on that, that's reasonable. And I don't know, Stephen, did you have anything that you take exception to there? Sounds like Stephen's in agreement then. Yeah.
All right, thank you.
Anyone else?
Hi, I had 2 questions.
Great.
Sorry, unfortunately I missed the first class because of registration.
Yeah.
I was just wondering if you could elaborate on the presentations, like when those will be presented or assigned.
Yeah, the mystery will be unveiled, I think, on Friday. I'm gonna make a list of different options for you all to sign up on a Google Sheet on a topic that I'm choosing, where you'll present 5 well thought out PowerPoint slides online to some schedule that I'll make rather arbitrarily. We'll be peppering them throughout the term, so some will be sooner than later, some will be later than sooner. And I'm saying 5 to 10 slides. 5 slides would be plenty, I think. I don't think we need more than that. And what we want is, I'm picking a geological oddity or point of interest in Alberta and having different individuals provide some background and interesting images from those based on those topics.
Thank you. And then just one other question. I was wondering if throughout the term, if it wasn't too much of an inconvenience, if you could give us suggestions on like good trails and campgrounds to see some of these points of interest that you speak about.
Yeah, I think the hope is to do that every lecture, to integrate the geology of the parks with the geological units that we're interested in. And I think I'd be most happy if we spent more time talking about the neat geological things you can see and do in Western Canada over anything else. So the answer is yes. That's what I want to do, and you know, it's the first time I'm teaching the course really, so I'm just kind of developing the materials we need to do that. But you know, nowadays, you know, like me and some of the other guest instructors I'm having come in, you know, we've been to a lot of the parks and provincial parks and national parks. We have a good background in these areas. We have a lot of favorite hiking areas, and you know, I've got all of my graduate students working each on a small project where they're each going to show you their favorite geological hike in lectures. So I'm hoping you'll have access to a lot of geological hiking knowledge by the time we're done.
Awesome, thank you. I'm excited.
Yeah, no, I'd be excited to put it all together too. I think it'd be great. Yeah, for sure. All right, I would say then, if there's no other questions appearing on chat or coming over the speaker, then I'm going to thank you for zooming in today, and I look forward to Isam's wondering what you're going to be tested in. There'll just be tests on the slides. I mean, right now we're talking about pretty general background stuff, right? I wouldn't think that the first two sessions, which are just professatory, are really emblematic of the materials for the course, right? So I think that we're just setting up a background. So, and maybe this question will be better asked in another week, I think is the right answer. But I'd like to just question you as to the things that are on the slides, and you know, maybe if I emphasize, well, we're talking about this, but you should listen carefully because I'd like to ask exam questions about it. I'll try to be upfront. I think some type of transparency for examination is okay. So yeah, let's see where this goes. We're just kind of, I think, all getting our feet wet in the class here, ISM. So. Okay, I think we're there then. And yeah. Yeah, I'm trying to figure out my teaching style too. Yeah, teaching by Zoom is a kind of, you know, we're going where no one's gone before. There's some things that are super cool about it, and some things that I'm not so sure about. I've no intention of using this course to lower your GPA. So even though the chair is sitting in on this class, I think he fully understands my intention not to be too tough on you all. I think you had a tough enough term already. All right, yeah, we'll see how it goes on Friday. I look forward to seeing you guys then. Okay, signing out.